Hi everyone, and welcome to Chem Talk, where today we will discuss how to calculate the enthalpy of a reaction using average bond dissociation energies. First, let's go over some background information. The process of breaking bonds is endothermic, meaning when a bond is broken, it absorbs energy from its surroundings. The opposite is true in forming a bond, as energy is released when a bond is formed. This makes the formation of bonds an exothermic process. For example, in order to separate these two hydrogen atoms, they must absorb energy from their surroundings. On the contrary, when a bond is formed between these two oxygen atoms, energy is released. But how do we know how much energy it would take to separate the hydrogen atoms, or how much energy is released when the bond between the oxygen atoms is formed? For that, we need to look at the bond dissociation energy. Bond dissociation energy is a measurement of how much energy it takes to break a bond and is typically measured in kilojoules per mole. You'll typically see it in a table like this. If we look at the table, we can see that it takes 436 kilojoules to break 1 mole of hydrogen-hydrogen bonds. We can also see that it takes 498 kilojoules to break 1 mole of oxygen-oxygen bonds. Since the breaking of an oxygen-oxygen bond would just be the reverse reaction of the formation of an oxygen-oxygen bond, we can just flip the sign of the bond dissociation energy to determine how much energy is released when an oxygen-oxygen bond is formed. Let's apply what we just learned. So for this problem, they want us to find the heat of reaction, delta H, when hydrogen and oxygen react to form water. When finding the heat of reaction using bond dissociation energies, we typically use the formula, the sum of the bonds in the reactant minus the sum of the bonds in the products. Or in other words, bonds broken minus bonds formed. The first thing to do is write out the reaction, but fortunately, this problem already gave it to us. Next, we want to draw the Lewis structures of all the reactants and all the products. This allows us to easily see every bond broken and every bond formed. So for this reaction, we have 2 hydrogen molecules reacting with 1 oxygen molecule to form 2 water molecules. The next step is to count how many bonds are broken and how many are formed, and then plug them into our formula from earlier. So for bonds broken, we have 2 hydrogen-hydrogen bonds and 1 oxygen-oxygen double bond. For bonds formed, we have 4 hydrogen-oxygen bonds. Next, we can plug in the bond dissociation energies from our table. So for hydrogen-hydrogen bonds, we can plug in 436 kilojoules per mole. Oxygen-oxygen bonds, we can plug in 498 kilojoules per mole, and 460 kilojoules per mole for hydrogen-oxygen bonds. Now, all we need to do is solve this equation, and we'll find that the heat of reaction is negative 470 kilojoules per mole of reaction. Let's try another problem. In the Haber process, atmospheric nitrogen reacts with hydrogen to produce ammonia. Use the given table of bond dissociation energies to estimate the enthalpy of the formation of 1 mole of ammonia. The first thing that we need to do is to write the balanced chemical equation. In this problem, we have nitrogen reacting with hydrogen to form ammonia. Normally, you would balance this equation by having 1 mole of nitrogen react with 3 moles of hydrogen to produce 2 moles of ammonia. But since the question asks for the enthalpy of formation of 1 mole of ammonia, we have to cut all of our coefficients in half to give us a coefficient of 1 for ammonia. This gives us half a mole of nitrogen reacting with 3/2 moles of nitrogen to produce 1 mole of ammonia. Now that we have our equation balanced, we need to draw the Lewis structures for nitrogen, hydrogen, and ammonia. Next, we need to count how many bonds were broken and how many were formed. For bonds broken, we first have nitrogen. Since we have a coefficient of 1/2 for nitrogen, and each nitrogen molecule has 1 nitrogen-nitrogen bond, we have a 1/2 mole of nitrogen-nitrogen bonds. Similarly, each hydrogen molecule has 1 hydrogen-hydrogen bond. And since we have a coefficient of 3/2 for hydrogen, that means we have 3/2 moles of hydrogen-hydrogen bonds. Finally, for our bonds formed, we have 1 mole of ammonia, which has 3 nitrogen-hydrogen bonds, which gives us 3 moles of nitrogen-hydrogen bonds. Now, we can plug in using values from the table. For nitrogen-nitrogen bonds, we can plug in 945 kilojoules per mole. For hydrogen-hydrogen bonds, we can plug in 436 kilojoules per mole. And finally, for nitrogen-hydrogen bonds, we can plug in 390 kilojoules per mole. The final step is to solve this equation, and we can see that the heat of formation of ammonia is negative 43.5 kilojoules per mole. Now let's talk briefly about how this is important. Bond energies allow researchers to find energy-dense fuels like liquid hydrogen by comparing the energy released during the reaction to the density of the fuel. Bond dissociation energies are also an indicator of the strength of chemical bonds, which allows researchers to develop chemically inert materials, like Teflon. Bond energies can even be leveraged between products and reactants to create more energetic reactions, like explosions. Now let's review what we learned in this video. When a bond is broken, it absorbs energy from its surroundings, which makes it an endothermic process. When a bond is formed, it releases energy, making it an exothermic process. Bond dissociation energy is a measure of how much energy it takes to break a bond. To estimate the heat of a reaction using bond dissociation energies, you follow these steps. First, write and balance the chemical equation for the reaction. Next, draw out the Lewis structures for all chemicals in the reaction. Then, count how many of each type of bond you have and plug it into the formula bonds broken minus bonds formed. Lastly, plug in the bond dissociation energy for each type of bond and solve to find the heat of reaction. That's all for this lecture. For more chemistry resources, please visit us at www.chemistrytalk.org.